lecture is going to be about using the things that we've learned the past week or two to model some real life stuff. Okay, so you have all the tools, we're just going to put them to use. So we're going to start with some exponential models. And first, we've seen the idea of continuous growth rates when we've been working with money, when we talked about continuous compounding. But actually, the idea of continuous growth can work in other contexts as well. So you can convert any exponential function, a times b to the t, into a continuous growth or decay function, a times e to the rt. So here's how the conversion works. We need a times b to the t to be equivalent to a e to the rt. I need these two things to be equal. So the a's are already the same, right? So I don't even need to really worry about that. Right? So I need b to the t to equal e to the rt. And I'm going to do a little trick on the right-hand side here. I'm going to rewrite e to the rt as e to the r to the t. Just taking advantage of one of the rules of exponents that says when you raise a power to a power, you multiply the exponents. So instead of writing e to the r times t, I'm writing e to the rt. I'm sorry, e to the r to the t. So if b to the t has to equal e to the r to the t, what two things have to be equal here? B has to equal e to the r. The two bases have to be the same. So this is how you convert from one form to the other. If you know b, you can figure out e to the r, and if you know r, you can figure out b. So b equals e to the r, or how would I solve this equation for r? B, if we take the log of both sides, let's take the ln of both sides. So if I have the ln of b equals the ln of e to the r, what is the ln of e to the r? R. It's r times the ln of e, and the ln of e is 1. So I have that r equals the ln of b. So this is how you convert. And again, the magic word is continuous. If you see the word continuous in a word problem, they're asking you to use the model that has e in it, a e to the rt. If you don't see the word continuous, use the other one, a times b to the t. And if your homework asks you to convert from one model to the other, these are the equations you use to convert. All right, so let's do an example. Cost of bottled water. In 1976, about 250 million gallons of bottled water were sold in the United States. Between 1976 and 2000, the bottled water industry had a continuous growth rate of about 12% a year. And this is a report to the New Jersey Legislature, Senate Environment, and Assembly Environment Committees. And in that report, they used this magic word, continuous growth. So I'm going to use a e to the rt. So t is representing time. The output of this is sales of bottled water. So maybe I could call it S for sales. I'll say, or G for gallons, because it's being measured in billions of gallons. Okay, so we're trying to come up with a model. They use the word continuous, so I'm going to use the model that has the E in it. And now I'm just going to plug in the stuff that I know. A is my initial amount, right? What is, how many gallons of water did we start counting at? 250 million, or 250 million, right? So I'm going to put this as a quarter, 0.25. And I'm just going to make a little note that we're measuring in billions. Okay. So I have 0.25 E My continuous growth rate is 0.12. Put the growth rate as a decimal, t. And then over here, I'm putting note t is measured in years since 1976. Because if we're using 250 million as my initial value, that means that 1976 is year 0. So t is measured in years since 1976, and g is measured in billions of gallons of water. So there's my model. And I decided to write use billions instead of millions, because you said it's 250 million, which is correct. But because it's growing, I decided to go with billions because it'll probably get into the billions soon. Any questions? All right. So now we're going to use this model to check a report that Beverage Marketing made. So this is like an industry or a group within the beverage industry, Beverage Marketing. They reported that in 2002, sales of bottled water were nearly 6 billion gallons. So let's see what our model says, how many gallons should have been sold in 2002. So here's my model, 0.25 e to the 0.12 t. And what should I plug in for t for the year 2002? Yes, 26. Because 2002 minus 1976 is 26 years later. So I'm going to do g of 26. And this is going to be a good check on the accuracy of my model. I'm going to see what my model predicts and compare it to what actually happened. And so this comes out to 5.66, which is in billions, right? Billion gallons. Does that agree with what was reported? Roughly, yeah. They said nearly 6 billion. They weren't being very accurate. Nearly 6 billion. 5.66 is nearly 6. So that's a pretty decent estimate. So we're pretty good up into 2002. And then let's see what the model predicts for 2007. So what number do I plug in for 2007? 31. Yep. So this would be 0.25 e to the 0.12 times 31. And you get, yep, 10.32 billion gallons. So that's a lot. We started with 250 million, and now we're already up to 10 billion in 2007. So it actually, if you look it up, the actual sales of bottled water in 2007 were 8.82 billion. What conclusions can you make? Sales have slowed. Yeah, because we predicted that it would get to over 10 billion by 2007, and it did not get there. Right, so sales must have slowed. Right, so a 12% continuous growth rate is seems to be no longer valid, which could be interpreted as good or bad depending on who you are, right? If you're the earth, it's good. If you're the CEO of a bottled water company, not so good. Okay, so I want to know when the model predicts that sales will reach 100 billion gallons. So let's write the model down. It says that G is equal to 0.25 e to the 0.12 t. And they're asking when, right? So the variable I'm going to be solving for is time. Yep. So where am I going to put that 100 billion? G, because that's representing gallons of water. So 100 in for G. And this is precisely the kind of equation we learned how to solve algebraically last class. So I would like you to do that now. Solve this algebraically. The first goal when you have a variable in an exponent, you have an equation that has a variable in the exponent, is to isolate the exponential expression. So I want to get this e to the 0.12t by itself. So I'm going to start by dividing out the 0.25. So we get 400 is equal to e to the 0.12t. Now we have a variable in the exponent. What do you turn to get variables out of exponents? What tool do we have? Logs. You can use any base, but I tend to always use ln. And when it's base e, it makes it even easier. So I'm going to take the ln of both sides. The ln of 400 equals the ln of e to the 0.12t. And the ln of 400 is just a number. I could put it in my calculator and get a decimal for it if I want. And what is the ln of e to the 0.12t? 0.12t. Yep, my bases match. This is log base e. Bases match. So I just lift off the exponent. So ln and e to the something, they undo each other. Right? They're inverses. So all you get is the 0.12t. Then just divide both sides by 0.12. And we get t is about, I think it was 49.9 years since 1976, right? Which would be the year, about 50 years after 1976 would be 2024. $1976 plus 50, 2026. So the year 2026. Or almost 2026, right? Do we think that this is an accurate prediction? Do you think that this will actually be the year that we reach $100 billion in sales of water?
Based on the last
100 billion gallons, yeah, thank you.
On the last question,
yes, based on the last question, this is probably not accurate because it seems that sales are slowing. And there's got to be a point where the market's going to saturate and you can't sell any more water. Right. Yes. Good point. Or there'll be no more space to put plastic bottles that the water comes in. So this is probably not accurate since sales seem to be slowing. All right, so that was an example of continuous growth. Now we're going to look at decay. So I already gave you a formula for radioactive decay, the m0 times 1/2 to the t over h. And you can convert it, just like any exponential function, you can convert it to a function that uses e, m0 e to the negative rt. Now, why in this case is r negative? We're in the last, because it's decay. Perfect. Okay, so I need to be able to make these two things equal. I want m0 times 1/2 to the t over h to be equivalent to m0 e to the negative rt. I want these two things to be the same. So the M zeros, they match already. Don't have to worry about those. So now I'm going to do the same little trick I did the last time where I exploit the rules of exponents. So I'm going to write 1/2 to the t over h as 1/2 to the 1 over h to the t. Because 1 over h times t would give me the t over h back. Okay. And I'm going to write e to the negative rt as e to the negative r to the t. So now the t's cancel, right? They're in the same place. So if something to the t equals something else to the t, then your two somethings have to be the same. So 1/2 to the 1 over h has to be the same as e to the negative r. Now this is just an equation. I could solve it for h or I could solve it for r. If you know one, you can solve for the other. Okay, so if you know half-life, you can solve for continuous decay rate, right? H is half-life. If you know continuous decay rate, you can solve for half-life. So let's solve for one of them. If I solve for r here, say I want to solve for r, what should I do? ln of both sides. So the ln of 1/2 to the 1 over h equals the ln of e to the negative r. And now I can apply, on the left, I can apply the rule of exponent, the rule of logs that lets me take this exponent and put it down in front. And I get 1 over h times the ln of 1/2 is equal to, what is the ln of e to the negative r? Negative r. So to solve for r, I just multiply both sides by -1. So I get r is going to be negative ln of 0.5, which I'm going to write as 1/2 over h. So I just multiplied those two fractions. So this is an equation you can use to convert. If you know half-life, plug in h and get r. WebAssign, your textbook in WebAssign uses a slightly different equation than this. So if you watch one of the Watch It videos, you'll see them use a slightly different equation. All they are doing to get that other equation, which is equivalent to this one, is they're going to apply the rule of logs that says when you take the log of a quotient, you can separate that into two logs with subtraction. So this is going to be negative the ln of 1 minus the ln of 2, right? The ln of 1 over 2 becomes the ln 1 minus ln 2. Distribute this negative sign. Well, first, but what's the ln of 1? No? Good guess, though. Use your calculator if you want. It's 0. The ln of 1 is 0 because when I put the ln of 1, I'm asking you e to what power will give you 1, and it would be the 0 power. Yeah. So ln of 1 is really just 0. And now when I distribute this negative sign, I get positive ln of 2 over h. So here's my formula for r. And if I want to know what h is, I can just multiply both sides by h and divide both sides by r. And I get a similar formula for h, which is the ln of 2 over r. So that's how you convert. If you know half-life, you can get continuous decay rate. And if you know continuous decay rate, you can calculate half-life. Now, it seems complicated, but here's how you uncomplicate it. There are two models, right? We have two models that are totally equivalent. This one and this one, right? This first one uses half-life, and the second one uses continuous decay rate. Whatever your problem gives you, use that model, use that version of the model. If you're given half-life, use the model that has half-life in it. Then you don't have to convert anything. Right? And if you're given continuous decay rate, use the model that has continuous decay rate in it. Then you don't have to convert anything. So that might help make things simpler. And some people just prefer to always use the same model. And then if you're given, say you really like this model with the half-life. If you're given continuous decay rate, then you just have to convert it to get half-life.
A lot of those web-assigned problems, they use 2 to the minus t over 8, which is so much more convenient.
You like that better than the half?
Oh, yeah.
Yeah, so that's a good point. M0 1/2 to the t over h. This is the model that I gave you, right? They use 2 to the minus t over h because all they said is, well, 1/2 is the same thing as 2 to the negative 1. Because this is 1 over 2 to the first, and you can move that 2 to the first into the numerator if you make the exponent negative. So then when you multiply these, you get 2 to the negative t over h. So that's another equivalent model that you could use if you like that one.
The logs and the elements are a lot more.
Oh, yeah. Yep. So you can have your favorite model. You can use a different model for whatever the problem calls for. So let's try one. We have radioactive radium. It has a half-life of 1600 years. So they've given you half-life. So let's use the model that has half-life in it. So my model is M0 times 1/2 to the t over h. And now plug in the stuff you know. I have a 22 milligram sample, so that's my M0. And my half-life is 1600. Put that in for h. And there's my model. So before we move on, just because I can and not because I would want you to, I want to show you that we could use the other model. Okay. So my other model is m of t equals m0 e to the negative rt. And I know m0, I just need to figure out what r is. And r, I figured out a couple slides ago, is the ln of 2 over h. So I'll just put that in my calculator. Ln of 2 over 1600. And I get 0.000433 approximately. Now I just plug that in here. I get m of t equals 22. That's my m0. E to the negative 0.000433 t. So I have two equivalent models, two different ways of saying the same thing. And just to show you that they really are equivalent, that they are exactly the same, I'm going to graph them both. So if we go to y equals, put the 1/2 version in y1 and the e version in y2. I made it so that the second graph would graph with a bold line so that we can tell which one's which. So for choosing a window, we just think about the problem. X is representing time, And this is radioactive radium that has a half-life of 1,600 years. That's a pretty long time. So you could choose a window like 0 to 5,000. That would give several halvings, right? Several half-lives will have passed. And then for Y, that's representing the amount of radium. And we started with 22 and it's decaying. So I went from 0 to 22 for Y. And then when you graph it, you see this is the one that has 1/2 to the T over H, Y1, and then we have Y2, graphing the E to the negative RT. And so you see that they're exactly the same function, just written in a different way. So now if I want to know when only 2 milligrams of the sample will remain, they're asking when, so I'm going to be solving for time. So I'm going to put a 2 in for M of T, right, for the output. And you can pick either equation because we just saw that they're exactly the same. So whichever one you want to use, you can go ahead and use that one. I think I'll use the E one. Any ideas why I chose the E1? Yeah, because the ln of E will just cancel. Just makes the algebra a teeny bit easier. So first thing we want to do, isolate the exponential expression. So I'm going to divide by 22. So we have 1/11 is equal to E to the negative 0.00043332 T. Now I have the variable trapped up in that exponent. To rescue it, I take the ln. Take the ln of both sides to get a variable out of the exponent. So the ln of 1/11 equals the ln of E to this power and then the ln of E to the something is just that something, right? You just lift off. We get negative 0.00043332 T equals the ln of 1/11. So divide both sides by this long decimal. ln of 1/11 divided by negative 0.000, oops, 4332. And I get 5,535 years. So this is the kind of thing that we only would have been able to solve graphically until this week. And now we can solve it algebraically. Questions? Sure, with the 1/2 one? Sure. So we've got 2 equals 22 times 1/2 to the T over 1,600. So the same principle, we want to isolate the exponential thing. So same first step is to divide by 22. So we have 1/11 is equal to 1/2 to the T over 1,600. Variable trapped in an exponent, take the log of both sides. I typically use the ln. So we're going to have the ln of 1/11 is equal to the ln of 1/2 to the T over 1,600. So now I can't just use liftoff because the bases don't match, right? ln has base E and my exponential is base 1/2. So I have to use the property of logs that says I can take this exponent and bring it down in front of the ln. So I have the ln of 1/11 is equal to T over 1,600 times the ln of 1/2. And now I've finished solving for t. I would divide both sides by the ln of 0.5. And I get ln of 1/11 over the ln of 1/2 equals t over 1600. And then multiply both sides by 1600. So my exact answer would be the ln of 1/11 divided by the ln of 1/2 times 1600. And when I put that all into my calculator, ln of 1/11 divided by the ln of 1/2 times 1600, 5,535 years. Other questions? Yep. Was slightly different. That's true. That is because when I solved it this way, this 0.00043332, I rounded this. Right? When I got that number, it was actually several more decimals long, and I rounded it. So this answer, the one I did this way, is actually off a little bit. The one on the next slide is more accurate. Good questions today. All right, so we're going to move on from exponential to logarithmic models. So logarithms are often used to scale very large or very small numbers into numbers that are easier to understand. So we're going to look at two common models, the Richter scale and pH. So just to give you an idea of what a log scale does, is it takes numbers that are really, really, really big or really, really, really small that are hard for us to sort of hold in our brains to think about how big they are, because all we can think is that's big, right? So it's kind of like when we talk about the national debt, right? The numbers are so large that it's hard for people to think about the difference between a trillion and 100 trillion. Like those are both just ginormous numbers, right? So what we can do is talk about the power of 10 that it is. Talk about the exponent. So let's say I want to compare 1 trillion and 1 billion, right? I want to know, those are both just big numbers, you know, more money than I could ever conceive of. So the way we can bring them down to numbers that are easier to hold in your head and think about is to talk about the power of 10 that they are. 1 trillion is 10 to the 12th, and 1 billion is 10 to the 9th. So it would be much easier to just think about the number 12 and the number 9, right? This just brings it down to numbers that are nicer, easier to hold, right? 12 and 9, much nicer, easier to compare than a trillion and a billion. So that's what a log scale does. It helps us compare numbers that are really big or really small by bringing them down to numbers that are easier for us to conceive of. So the first log scale we're going to look at is the earthquake magnitude scale, the Richter scale. What's an example of a number that might be used to report the magnitude of an earthquake? 7.2. Yep. You might hear 7.2 on the Richter scale. Or, you know, you might hear 4.1, something like that. That's a little one, yeah. 7.2 would be a big one, though, right? But the difference between those numbers doesn't seem that big. They're all off by less than 3.
You're not the one one standing under the building.
Yeah. So seismologists generally determine the Richter scale magnitude by looking at a seismogram. This is just an example of one. It defines the magnitude of an earthquake as a log function. You take the log of the intensity of the earthquake, which you measure from the seismogram, which is measured, I believe, in, oh, I forget the units, but it's amount of movement of the earth, like how much earth is displaced, right? So, and it's a very large number. It will be a very large number, the intensity. So they take the log of the intensity of the earthquake divided by a standard earthquake, which is the smallest intensity that's detectable by the machine, by the seismogram. So we take the log of the earthquake intensity divided by a standard intensity. So here's a little example. In 1906, there was a devastating earthquake in San Francisco. It had a magnitude of 8.3 on the Richter scale. And at the same time, in Japan, there was an earthquake with a magnitude of 4.9, caused only minor damage. So we want to talk about how many times more intense, and intensity measures actual Earth movement, right? How many times more intense was the San Francisco earthquake than the Japan earthquake? So I'm just going to do a little calculation for each of these. San Francisco, well, magnitude is equal to the log of intensity over standard intensity, right? And I want to talk about how many times more intense was the San Francisco than the Japan earthquake. So I want to know something about the intensity of San Francisco. Right now, I only know its magnitude. So I'm going to replace m with an 8.3, and I get the log of I over s. So I now have an equation with a log in it. If I were to change this to an exponential equation, what would it say? Yes, 10 to the m, because this is base, right? This is base 10 if I didn't write it there. So 10 is the base in both equations. Logs are exponents, so my 8.3, or whatever the magnitude is the exponent, equals I over s. The input of the log is the output of the exponential. So then if I just finish solving this thing for intensity, I get s times 10 to the 8.3. Just multiply both sides by s. All right, you take a minute or two. I want you to do the same thing for the Japan earthquake. Solve for its intensity. What was the intensity of the earthquake in Japan? What was the magnitude? 4.9. Okay, so just replace the m with a 4.9. Change it to an exponential equation. What do you get? Uh-huh. You can just tell me. 10 to the 4.9 equals I over s, and then multiply both sides by s, and you get s times 10 to the 4.9. Okay, so this is the intensity of my San Francisco earthquake. This is the intensity of the Japan earthquake. So the question was, how many times more intense was the San Francisco earthquake than the Japan earthquake? So how do you figure out how many times bigger something is than something else? Divide, yeah. Like, exactly. So if I want to do the intensity of San Francisco over the intensity of Japan, I have S times 10 to the 8.3 over S times 10 to the 4.9. The S's cancel. And then when you have like bases, you subtract the exponents. So this is going to be 10 to the 3.4 times as intense. Right. So that is 10 to the 3.4, 2,512, we'll say. 2,512 times the intensity. 2,512 times the amount of Earth movement.
Well, there's also something to do with heat waves and constants of it. If the building, if the wave under the building is exact heat wave, the building will just come down and crumble.
Yeah.
If there are different waves, the building will stand.
Yeah. You actually debated of having one of your projects this semester have to do with looking more closely into earthquakes, but I didn't do it. So that's way more intense, right? It looks like the numbers aren't very different, 4.9 to 8.2, or to 8.3, but that is a big difference in intensity because those numbers are exponents on 10, right? They aren't just the measurements themselves. So increasing the moral, this is how the Richter scale works. If you increase the magnitude by 1, like a 5 to a 6, or a 4.1 to a 5.1, that means you increase the intensity of the earthquake by a factor of 10. 10 times as intense. All right, so our next model is about measuring acidity using the pH scale. So this one is sort of a little bit different because we use a log scale here because the numbers are really, really, really small, right? Lots of zeros, they're just on the other side of the decimal point. So chemists use log scales to measure pH, which is acidity or alkalinity. pH values are generally between 0 and 14, and 7, which is water, is considered neutral. Less than 7 is acid, and greater than 7 is a base. So this is the formula. pH is just the negative log of the concentration of H+ ions. And this notation, this is just a chemistry notation. H+ is a symbol that they use for hydrogen ion, and square brackets is what chemists use to represent concentration. So they measure concentration in moles per liter of a solution. So if you aren't a chemist or haven't taken chemistry and you don't know what that is, you can still solve the problem. It's just moles is a unit, liters is a unit. It would be like saying grams per liter or something like that, but moles is a different kind of unit. All right, so if we want to find the pH of shampoo, and we know its hydrogen ion concentration is 7.4 times 10 to the negative 10, all we do is plug that into the formula. pH is the negative log of 7.4 times 10 to the negative 10. And that's just a very, very small number. 7.4 times 10 to the negative 10, that means take 7.4 and move its decimal point 10 to the left. So it's 0.00000000074. So if I take the pH of it, I get negative log 7.4 times 10 to the negative 10. Make sure you put parentheses around the exponent of negative 10. I get 9.13. That number is just so much nicer than saying 0.00000000074. We say, instead of saying that's its hydrogen ion concentration, we can say, well, it has a pH of 9.13. Much easier number for us to conceive of. And that would make it a base. Right. Shampoo generally is pretty sudsy. that make sense? All right. Okay, so here I have, this is a kind of beer, giving you its pH, so it's acidic. I want you to find its hydrogen ion concentration. All right, so let's see, pH is equal to negative log of the H plus concentration. You can just call that X if you're unfamiliar with the chemistry notation and it looks confusing to you. We could just call that thing X. pH equals negative log of what? Right. So pH, they told me was 4.1. So I'm going to replace pH with a 4.1. And then if I try to switch it to an exponential equation now, the question comes up, what do I do with the negative sign? Right? So what I could do is start by dividing both sides by -1. So I have negative 4.1 equals log X. And then this is base 10. There's a little imaginary 10 there. So when I change this to an exponential equation, my base is 10. My exponent is negative 4.1 because the log is the exponent. Negative 4.1 equals X. So there's my answer. You could just leave it like that, 10 to the negative 4.1. Or you could put it in your calculator. And because this is kind of a sciencey example, maybe we'll put it in scientific notation. So 10 to the negative 4.1. And I get 7.94. And this E means times 10 to the. So this is 7.94 times 10 to the negative 5. Yes. This is moles per liter. Hydrogen ion concentration.